Hi, everyone. This is going to be part 2 of your Unit 1 notes. So again, you're not going to turn in these notes yet. We're going to turn them in all en masse at the end of Unit 1. So today we're going to be talking about moles, molar mass, and then empirical molecular formula. So starting out with moles, that's something that you should already know. 1 mole is the amount of a substance that contains the same number of entities as 12 grams of carbon, aka it's Avogadro's number. You took chemistry last year or the year before that, you use this number a lot, or you use molar mass a lot. So basically what it is the SI unit, or the standardized unit for the amount of a substance, and it specifies the number of objects in a fixed mass of that particular substance. So we have 1 mole of carbon is 6.022 times 10 to the 23rd carbon atoms. 1 mole of water is 6.022 times 10 to the 23rd water molecules. So again, we're seeing molecules versus atoms here. But if we have 1 mole of water, that means that I have 2 moles of hydrogen and 1 mole of oxygen within that molecule, right? Because our subscript of 2 means that for every 1 water molecule, there's 2 hydrogens. And for every 1 water molecule, there's going to be 1 oxygen, okay? The atomic mass listed on the periodic table is going to be an average of the masses of the naturally occurring isotopes, but we can also use that number as molar mass of that particular thing as well. So moving on to this should look pretty familiar, or at least strike a chord with you, because last year we used the mole map, which looked a little bit different, I'll grant you, but this one's a little bit more extensive. So if we're in moles and I wanted to go towards mass, what I would have to do is multiply by the molar mass. If I wanted to go from mass backwards, I would divide by molar mass. If I want to go from moles to volume at standard temperature and pressure, I'm going to multiply moles by 22.4 liters. And if I want to go backwards, I'm going to divide by 22.4 liters. Going from moles to particles requires you to multiply by 6.022 times 10 to the 23rd power. Going backwards requires you to divide by 6.022 times 10 to the 23rd power. This one here has to do with molarity. So if we recall, molarity is how many moles over the liters that you have. So if you are 1 molarity as a compound in solution, that means that there is 1 mole of that compound in 1 liter. If you were 2 molar, you would have 2 moles of that compound in 1 liter of solution, and so on and so forth. So to go from moles to solution volume, you would have this set up here, and to go backwards from solution volume to amount of moles, you would have that set up. We will go over this in a little bit because that's not something we did a whole lot of last year, or the year before that, for that matter. Moving on, we have a couple of real quick examples to just kind of get your brain thinking a little bit. Example 1 states that 1 iron atom has a mass of 55.85 AMUs, and 1 mole of iron has a mass of 55.85 grams. Therefore, 55.85 grams contains 1 mole, or 6.022 times 10 to the 23rd atoms. And we know that that's true, right? Because I just said that the average atomic mass is not only in AMUs, but also grams, because 1 mole of any particular atom is going to weigh the same numerically as the average of all the isotopes. And then down here, we have 1 molecule of water has a mass of 18.02 AMUs, and 1 mole of water, 1 molecule of water has this many AMUs, and 1 mole of water having 6.02 times 10 to the 23rd molecules has a mass of 18.02 grams. So again, they're saying basically the same thing. It's just 1 is an atom and 1 is a molecule. Okay. Molar mass. So that is going to be the mass per mole of whatever it is entities. So if I had 1 mole of atoms, 1 mole of molecules, 1 mole of formula units of whatever it is, the mass per mole is going to be the molar mass. The unit for it is grams per mole, because again, however many grams 1 mole of that substance weighs is its molar mass. So if I wanted you to find the molar mass of this compound right here, We know based on the subscripts that there's 2 sodiums and only 1 oxygen because that one is implied. So we would take the average atomic mass on the periodic table multiplied by 2 for sodium because there's 2 sodiums, and then add that to 1 oxygen mass, and we end up with 61.98 grams per mole for this compound. Next, there are some sample problems. So what I would very much like for you to do is pause it here and try these on your own, and then I will walk you through them after that. So again, pause, try them on your own. All right, so hopefully you followed my instructions and you paused it and try to work these out for yourself. So let me explain what I have here on the screen. For this problem, it asks me how many moles of calcium, and then it gives you a formula, are in 43.67 grams of that compound. So this is calcium phosphate. So the first thing you have to do is figure out how many moles of that compound there even are. So that's this first step here. I take what I'm given, my given number, and that's 43.67 grams of calcium phosphate. And I am going to move from grams into moles. So by doing that, I'm dividing by my molar mass, which I'm able to calculate using the periodic table and adding all that together. And then finally, the second step is how I figure out how many moles of calcium are in that specifically. So what I did here was this step right here moved me into moles of the compound. But I know in this compound, there are 3 calciums for every one of that compound. So that's here. There's 3 moles of calcium for every 1 mole of the compound. So ultimately, we multiply our molar amount by 3, giving me this answer. That is going to be rounded to 4 significant figures because our original number had 4 sig figs. Letter B, how many formula units of calcium phosphate are there in 43.67 grams? So again, we're starting out with our given number here. And we're going to convert into moles doing the exact same procedure that we just did. 1 mole over 310.98, or yeah, 0.98 grams it's supposed to be. Then, since we're moving into formula units, that's where we use Avogadro's number. So for every 1 mole of anything, there's 6.022 times 10 to the 23rd formula units. So if we multiply that out, 43 times this, divided by what's on the bottom, we get this many formula units. Okay. And then I believe that I forgot to put the times 10 to the information on that. So that's my mistake, but this would be times 10 to the something or other. I believe it's 40, or not 40, sorry. I believe it's 22, if I'm remembering correctly. So my apologies for that, but 8.478 times 10 to the 22nd formula units. This last one required a little bit of figuring on your part. So it asks how many moles of carbon are contained in 33.64 grams of ethanol. You have to know what ethanol is and know how to draw it to figure out what your formula is. So ethanol, ETH, that means that there are 2 carbons. So carbon 1, carbon 2. That all suffix means there is an OH group bonded on there. And if we remember how many times carbon can bond, we're going to imply our hydrogen. So this carbon on the end has space for 1, 2, 3 hydrogens. This one in the middle has going to be space for 2 hydrogens, and there's 1 over here, giving me my formula C2H6O. So now we can use that and we can do a calculation. I start with 33.64 grams of my C2H6O because that's what the problem tells me. I'm going to divide that by the molar mass that, again, I calculated on the periodic table. And with my formula, I know that for every one of these molecules, there are 2 carbons in it. So now I can calculate how many moles of carbon specifically there are in every this many grams of that. Okay. Now, if you have questions about that, you don't know where I got some of my numbers, please, please, please talk to me. Please talk to me. I'm not scary. I'm happy to help. So moving on to percent composition or mass percent. That is basically going to be you guys figuring out what kind of percent any particular part of a compound is of that entire compound. So our formula here, mass percent, is going to be molar mass of your element divided by molar mass of your compound. Now, I'm going to say about molar mass of your element, if there's more than one of that element in the compound, like this, that top number is going to be multiplied by how many of that element are in the compound. So if I was doing mass percent of carbon in this molecule, I would put on the top 2 times 12.01 over my total molar mass of that compound. Okay, so do not forget that because that will get you a wrong answer. So we have a sample problem. How many grams of carbon are in 1.7 kilograms of ethanol? So we're using the same one as before. So this is going to factor in percent composition. It's going to factor in you being able to interpret a few things. So once again, I want you to pause here and I want you to try to solve this problem. I want you to try to solve the problem. Okay, so once again, hopefully you followed instructions. So this is going to require a couple of different steps here. So let me explain. First of all, our given number is 1.75 kilograms of ethanol. So we have to convert that to grams first. So that's an easy metric conversion. We know that for every 1 kilogram, there's 1,000 grams. So we just multiply 1.75 by 1,000 and we get this many grams of ethanol. That's the easy part. Now, we do mass percent, right? Because we want to know specifically how many grams of carbon there are. So we need to figure out what percent of that compound carbon is. And we already figured out the formula in the previous problem. So we know that in this particular compound, there are 2 carbons for every molecule. So we have 2 times 12.01, which is found on the periodic table, divided by the mass of the entire compound. And that gives us 0.5214, which is about 52.14%. So that allows us to multiply that decimal number by how many grams of the entire compound we have to get how many grams are represented by only carbon. Because remember, if carbon is 52.14% of that molecule, it should also be 54.12 or 52.14% of any amount of that molecule. Okay. So again, if you're confused, please seek me out. Empirical formula is next. What that is the simplest or most reduced whole number ratio of the atoms in any particular compound. So a quick example I can give you would be glucose. Okay, so the formula for glucose is C6H12O6, right? But that's called a molecular formula. That's the actual formula of that compound. But the ratio of carbon to hydrogen to oxygen is actually 1 to 2 to 1, right? So that's all it is. An empirical formula tells you the ratio of one atom to another in any particular compound. So we would write this empirical formula CH2O, but we know that that's not the real formula of glucose. This one is. So if you are trying to find the empirical formula of something, you're going to start by converting the gram or percent or whatever they give you to moles using the molar mass of whatever compound. You're going to divide all mole values by the smallest value of moles. You're going to round to the nearest whole number if it is less than 0.2. Otherwise, you're going to multiply to get to a whole number integer. And if you're ending up multiplying, then you're going to use this. So if you end up with a number that's 0.25, you're just going to multiply everything by 4. If you get 0.33, you're going to just multiply by about 3. If you get 0.5, you'll multiply by 2 and 0.75 by 4. And I know that you're probably thinking, what? But I will show you through an example. Worry not, I will show you what to do. But before that, we have to talk about molecular formula just briefly, which again is the real formula. So if you have an empirical formula and you want the molecular formula, basically taking glucose again, C6H12O6 and its empirical formula, to get from that to the molecular formula, which again is this one, all you have to do is multiply all of those subscripts by a whole number integer. In this case, we would multiply this entire thing by 6, right? Because this implied 1 here, 6 times 1 is 6, 2 times 6 is 12, and again, 1 times 6 is 6. So that whole number n is going to get us from our empirical formula to our molecular formula. Okay? So let us do another sample problem. So again, you are welcome to try this on your own, but I will not blame you if you just kind of walk through it with me. Okay, so what I have just put on the screen here is the first step. So if I want to take all of this and I want to convert towards empirical formula, I am going to assume that I'm dealing with 100 grams of whatever compound, because that's going to make my life easier. That's going to mean if I have 100 grams of this compound, that my 40% carbon turns into 40 grams, and my 6.71% hydrogen turns into grams, and my 52.29% of oxygen turns into grams. So by assuming you start with 100 grams, you just make your life simple. So if I'm starting with, again, my 40 grams of carbon and I convert that to moles, I get 3.33 moles. If I start with my 6.71 grams of hydrogen and I convert to moles, I get 6.66. And last but not least, by 52.29 grams of oxygen and I convert to moles, I get 3.268. So now I've converted to moles, which is great. So what I need to do next is I need to divide every single one of these mole amounts by the least amount of moles that I ended up with. So if I look at my numbers, this 3.268 is my least amount. So I'm going to divide every single one of these by 3.268. Okay, and my top number, I'm going to get about 1 for that. For this second one, I'm going to get about 2. And for this third one, I'm going to get exactly 1, right? So what that tells me here is that for every 1 carbon, I'm going to have 2 hydrogens and I'm going to have 1 oxygen. So this here is my empirical formula. My empirical formula is CH2O, just like the empirical formula for glucose is, but it can also be the empirical formula for lactic acid. Now, my next step, and I'm going to switch colors for this, my next step is to figure out what the mass of this empirical formula is. So that's going to be 12.01 plus 2 times 1.008 plus 16. And that's going to give me what? I think that's 30.03-ish. So that's, again, the molar mass of the empirical formula. I'm given the molar mass of my molecular formula, 90.08. And if I divide that by 30.03, I'm going to get about 3, which means that I can multiply this empirical formula by 3 to get C3H6O3 as my molecular formula. So all that I did was I took a bunch of percent information, I converted from grams to moles, divided by my lowest molar amount, got my empirical formula, used my information about my molecular weight of lactic acid, and converted to my molecular formula.